Have you ever wondered how Redis survives when even half of its nodes are on fire? All thanks to something called consistent hashing. And no, it's just not a cooler name given to a mod and function. In my last video, I walked you through how consistent hashing works and how systems like DynamoDB, Redis Cache, or Memcached rely on this. In this one, we are going to build step by step in Golang from a bare bone consistent hashing to having virtual nodes and finally fully replicated fault tolerant setup. So you have seen the theory. Now let's build it. Rome wasn't built in one day. Neither was a distributed cache that can handle 1 million requests per second. Hence, we will also start small by building our first implementation of hash ring, which is just simple bare bones setup, where every node and key are hashed and plotted on a circular lines. Think of node as a shelter home and keys as traveler. These keys can only move in the clockwise direction and find their first shelter home. You might already be thinking that's cool, but let's start implementing. Hold on that thought. Don't jump into keys yet. First, figure out how you can add a node to our ring. Here is a little challenge for you guys. What data structures can you use that can help you have a best optimization on doing a binary search and can also be represented in a circular pattern? All right, let me show you how I implemented it. And if you have got a cleaner approach or solution, hit me up in the comments and let's level up together. Now, the hash ring that we want to create contains a configuration, right? That can be configured by user. So over here in the configuration right now, we have enabled the hash function, whatever hash function the user wants to use, right? Then the two major elements that we are interested right now to discuss is a map of nodes where the key is your hashed value for the node and the value is the connection object to the node. Then there is a sorted list of keys, or this keys is basically the hash value. Now, why sorted is just to enable us to have a better search operation whenever we want to store a key, right? Now, let's go ahead and first see how we are adding a node to this. So, whenever there is a call to add a node, we get the node or connection object, we find the hash value for that node. And if that hash value doesn't exist in the hash ring, that then we know that we will want to add that node to our hash ring now. So as soon as we find out that the node doesn't exist currently in our hash ring, we store that node with the connection object in the node's map and also add that to a sorted list. The hash object basically, the hash value in the sorted list, right? This is how we add a node. Now we know that we have a array which contains all the hash maps, hash values for the nodes. If we want to get any key or save any key, we want to search this sorted list, do a binary search on this sorted list, find the hash value which is greater than or equal to the hash value of the key, right? So that's how we have implemented the get method. This get method ask for a key that you want to store. That's your traveler that we are discussing, right? So we accept the traveler's name, we find the hash value for the traveler, we do a search operation where that traveler can fit in. What's the next highest value for that traveler? A best shelter home, basically. And as soon as we get that value, we extract the connection object from the node's map and we return that to the caller. So the connection object is being returned to the caller back, and now it's up to the caller whether he wants to do an update operation, delete operation, or insert operation of this key. It's up to the caller. We have just returned the connection object. Similarly, while removing a node, we first want to find a hash value for the node that we want to delete, right? And then try and find if that node exists. If the node exists, we'll remove it. And while removing, we remove that node's hash value from that sorted list also. so that we are sorted. Next time, if we want to get a node for a particular key, we don't have to search in this sorted list, right? We don't want this node to be there in the sorted list. That's the bare minimum setup for a hash ring. Okay, let's say you have built this hash ring. You added few nodes to it, and even got it working. But soon it will start cracking. Why? Because the function that you have used over here is not uniformly distributing these nodes. Neither it guarantees that the keys that you'll add will be uniformly distributed, creating the problem of hot nodes, where one node is overly worked. That creates problem where you rely heavily on one particular infrastructure, and if it fails, everything will shatter. So what is the solution to this? Solution is using virtual nodes. If you've seen my previous video, you would understand why virtual nodes is important and how it is solving the problem, right? I'll give you a very quick introduction of virtual nodes. Virtual nodes is saying that this single node or single infrastructure will be sitting at multiple places in the hash ring. That will help you distribute the keys evenly. That will help reduce load on one particular infrastructure, hence solves the problem of hot nodes. Now let's bring that into code and see how you can solve the problem of consistent hashing using virtual nodes. Okay, to our existing bare bones hash ring implementation, I have just added one configuration that represents the number of virtual nodes that you want to create for the actual existing node that you have. So that is the number of virtual nodes per actual physical node, right? Now, to our hash ring, I have introduced one more map which contains the actual host that we have in our system, which is actual host ID or the hash value for that host when it was added to my system. Now, let me take you through the add method and the remove method because those two methods are the only methods that are impacted by this implementation. So let me open these two in a side-by-side configuration so that it makes it easy for you to understand what is the basic difference between the two. So on the left side, you can see that I have opened the method that adds a node, and on the right side, I have opened the method that is responsible for removing the node. Now, when we are adding the node, our first responsibility is to understand if that node exists in the list of hosts that we already have, right? If it doesn't exist in the host, then we are ready to add that. So then what we'll do is we'll run a loop on the number of virtual nodes that we want to add. We'll start creating the node ID where we'll append the actual node identifier along with the number of the iterator number of virtual nodes, and then we'll keep adding that to our hash rate, and that's how we get our all virtual nodes ready. And in the end, we'll just also sort array that we had of all the virtual nodes now, right? That's how we get one node placed at 10 different locations or 5 different locations according to your configuration in the hash ring. Now, when we want to remove it, that's the same process, but right now, instead of adding or storing it to the hash ring, we'll start removing it from the hash ring. So that's how the delete or remove node happens in the virtual node setup. That's very easy, right? Easy to extend because we had a basic implementation of our hash ring. Now, by this time, we already know that this has an issue. Because let's say if we have actual 4 nodes configuration, right? And if node 1 has 1,000 keys saved and this node 1 is is removed or it dies out, right? And that's very normal for any server to get exhausted, right? So if this node goes out, what will happen to the values that were stored? We have not created a backup copy yet, right? So in the next section, we'll fix this problem by introducing a concept of data redundancy and how we can utilize the hash ring to implement data redundancy in our system. What is that one concept that comes to your mind when as soon as you hear data redundancy or copying the data into multiple nodes? Yes, I know. That is, of course, that you need to add more nodes to your system, right? But if you do that, you'll get a lot of pushbacks. Now, there are reasons to it. First would be budget. Then is your infrastructure limit. Because if, let's say, your original system has 200 nodes deployed already, you cannot have copy of each and every of these 200 nodes, right? You cannot maintain that infrastructure. But then again, there is one technical limitation also to this. Let's say if the client says that we are open to the budget and you want to do it, then also you will not be able to do it. Because these backup nodes will not end up at the same location of the original node, right? You cannot guarantee that the hash value of these backup nodes is also equivalent to the hash value of the original node, right? So how will you do it? So the solution to this is very simple, that you maintain the copy of this data into the consecutive nodes of the master node. Now, by consecutive, I mean the next node that comes in the clockwise direction in the hash ring. So you maintain two, three, or four copies of this same data into those nodes which are consecutive after this master node. Now, this gives you a very good thing, that is, you have implemented a false safe switch where if your master goes down, the next consecutive node is always ready to serve the data for that particular key. How will you do it? So there are a few things that will change in our existing implementation. First thing is adding another configuration for a field which says that how many copy of this data you want to maintain. Then is we'll create a function which returns a list of nodes. Instead of just returning one node, it will return a list of nodes which will be responsible for saving the data. So we'll introduce a function that will be called as get nodes for the keys, and it will return multiple nodes. Now let's go to the code and see how this will be done. Okay, now you can see that I have two methods implemented over here. One is get the primary node. This will be helpful when you want to get the primary node which will serve the request for the user. That means if you want to get the key, right, in which node that key is available, that's when you'll call this function. Then you have a get nodes for key. This will be utilized in place when you want to add the data to the system, right? And also delete the data from the system. So that is when this function will be called. Now, what is this function doing? Let's debug this function and understand how we are capturing multiple nodes. Now, let's say I have introduced one more configuration, that is replication factor. So, for example, let's say they need three replication or four replication. It depends on the configuration that the user wants, right? Now, this when we go ahead and we receive a request, we'll generate the hash value of the key that user wants the nodes for. Then we'll create an empty list of nodes. So this empty list will be returning. This will be the final value that we'll be returning to the user. Now our task is to fill this list. So firstly, we have a starting point of starting node, which is the master node basically. And starting from the master node, we keep finding the next node. We keep incrementing and we keep finding the next node. And that next node, the next node should not be a virtual node. It should be an actual node. Because if you make a copy of the same data on the same server, basically, if you make two copies, it is of no use, right? So that's what we are doing with scene hash map. So scene hash map will contain all the nodes that we have already populated. So this is to validate that we are not going to the same node again, and we are doing a unique. We are returning unique list of n different nodes. Now this particular logic I have added specifically when, let's say, your application factor is 10, but you only have five nodes available in the system, and rest all nodes have already vanished out of the system. So why do you want to do a infinite circling to find next nodes? It's better to return from there, right? You know that there are only five nodes. Even if I need 10 replication factor, I cannot achieve it, right? So let's break out. So that's what this condition is. And as soon as we have any element in the node, we have at least one node where the data has to be saved or removed from, we return that data. That is plain and simple. And the caching server who is utilizing this hash map will call this get nodes for the keys at two places, basically. One is when it wants to delete the data, one is when it wants to save the data. But if it wants to perform a get operation, the recommended way is get the primary node. So I think all of you are ready for the moment of truth. Let's plug this hash ring into the caching server and see how caching server has to utilize this hash ring. Now, I've already written the code for caching server so that we can reduce the time of the video and to focus on the implementation detail. Now, in the caching server, I have two functions which are like adapter functions to call the get node and get multiple nodes function. Now, this from definition, we know that this get node function will be called at only one place, that is when we want to get data of a particular key, right? And get nodes will be called two times. One is when we are deleting the data, one is when we are putting the data, right? Now let's see if they are really called in those two places. So you see this delete function. While deleting, I get a list of nodes and I run a for loop on all the nodes. Now let's go to the get function. Now get function calls the get one node and it tries to fetch the value from that one node. And same if you go to put, put is again calling the get all nodes, basically the nodes where the replication has to happen, and it tries to perform the put operation in all the nodes. So I'll add the link to the code in the pinned comment below. Now I want you guys to fork the repository and try running this a caching server and see this in action. Now, what we have done till now, let's do a quick recap. We have built a bare minimum consistent hashing ring. Then we went ahead, improved our functionality by adding virtual nodes. And then finally, we also implemented data redundancy to safeguard our implementation from failures. We have also plugged this hash ring into our caching server, and we have seen that everything works fine till now. Now, what we are already missing? These nodes, when have to implement a gossip protocol. Now, what is gossip protocol helps in? Now, let's say when one node goes down, the next consecutive node is available to serve the request. But what if when we add another node, it gets into middle of the two existing nodes? Now, this second node has to maintain a copy of the data, right? Which it has to serve or do some reshuffling of the data that was already present in the next node, right? Because now my hash ring will pinpoint some keys to this newly added node, right? So this thing has to be implemented. That is what gossip protocol takes care of. So each of these nodes keep talking to each other to see that if there is any change in the configuration of the node. And if there is any change, it will do the minimum shuffling that is there with consistent hashing. Then we need to maintain the atomicity of the data. So when you're doing a put operation, you need to make sure that the put operation completes successfully in all the copy nodes, right? You don't want your data to be updated in one node where and not in the other nodes, right? Because then that will be a stale copy issue again. Then no clients wants to wait for you to copy the data into three different places or delete the data into three or four different places. They only want you to do it at one place. They don't care if you're doing data redundancy, right? So you have to implement something to synchronize data between these redundant nodes, right? So these three things are the major things that are missing right now in this piece. And that's when you come in. Now, I want you guys to fork this repository, implement or fix these three things or any of these three things, and ping me that on the comment section below. And we'll collaborate to understand if there are something that can be improved or if it is good. If it is good, I'll try to merge that in the repository so that it helps the other fellow developers to improve. So, my friends, if you have reached this far, you should clap for yourself because you are well versed with basic implementation of any distributed cache. And you also understand how consistent hashing is working and how that can be plugged in into different systems now. If you found this helpful, please hit like button, subscribe to this channel for further updates, and also drop a comment below on the feature that you'll implement next, whether it is gossip protocol or asynchronous write or good read operations. I read every comment and I would love to see your version of this system. Also, the complete code is on my GitHub repository where I have added that link to the GitHub repository in the pinned comments below. You can fork it and break it to improve it. Let's see you in the next video.